What we're looking at in this video is something called character sets and also character encodings. And the problem we have in computing is that computers work with ones and zeros and humans work with real letters and numbers. So how do we get these letters like A, B and C stored inside a computer that only stores zeros and ones? And so the way we do it is to map a particular letter. So for example, we could map the letter A to a particular number in binary. And there's no reason we couldn't say that A is that number in binary. And we store that number and then that translates into an A. And what we need is a way which is common amongst different computers, different software, so that computers can talk to each other and so that the software can be made to work with each other. And so one of the earlier ways of doing this was something known as ASCII. And that stands for American Standard Code for Information Interchange. And this was a way in which we could represent characters, which are also known as glyphs. And so I could represent, for example, the letter capital A with the binary code 1000001. And the decimal equivalent, that would be 65. So the number 65 in binary represents the character capital A. And I'm not showing the whole table here, but if we went down further, we'd find the small letters as well. And you can actually try this on your keyboard because there's still some of this left over today. If you were to type in Alt and 65, you would get a capital A. I'm assuming that you're using a Windows operating system. I'm not sure whether it works on others. If you were to type in, for example, let's find less than here. So if you type in Alt and 60, then the less than sign appears. And you can get characters like E, the French E acute accent by doing this method. So that's what ASCII is. It's a way of laying out and saying that certain characters, certain English alphabet characters, can correspond to a particular binary. Now we do have to consider when we think about these how many characters are available within a particular system. Now we need to consider how many possible characters we can encode with a certain number of bits. So in ASCII we have a 7-bit encoding, and that will go therefore from 00000000 all the way up to 1111111. And so in decimal that is from 0 all the way up to 127. So because 0 is another option, we therefore have 128 characters that we can encode with ASCII. Now in the English alphabet we've got 26 small letters, 26 large letters, that's 52. We've got 10 digits which we use for numbers, so we need at least 62 characters. And then you've got others like a space and speech marks. So we can easily encode all of the letters of the English alphabet into 128 characters. Some other languages, early on, they realised that ASCII alone wasn't good enough for things like the Greek alphabet. So what they did was they did extended ASCII. And this often included other strange characters like a block or a half filled in block. And this gave us another 128 characters. Extended ASCII was 8-bit or 1 byte. So each character needed 1 byte and used extended ASCII, and that gave us 256 characters. Which sounds like a lot, but some languages, like Japanese and Chinese, have literally thousands of characters inside them. The Japanese language, typical Japanese person will probably understand around 3,000 to 5,000 characters, and Chinese possibly 30,000 to 50,000 characters. So these systems were not enough to store all of the characters that are available in the world. So what they developed was a new character system called Unicode. And Unicode, there are two sorts of Unicode. One is a 8-bit Unicode, so 1 byte. And then there's something called double byte or 2-byte Unicode, which is 16-bit Unicode, and that takes up 2 bytes. And Unicode is now what we're looking at. So let's take the example with some Japanese. And so we're going to look at the Japanese characters which say hello, or actually they say good day. So this character here means now, and that says konnichi, and then the character here wa. So this says it roughly, if we write it in English, kon, and then nichi, and then wa. Now the question is, how do we encode this in Unicode? So if we take a look at the Unicode here, this here is the Unicode. So we're looking at 4EC0 as the column, and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's A. So 4ECA will equal the character kon. And this is hexadecimal here, which we're using as our counting system. And if we go on to see the next one, which is nichi and wa, then nichi here is 6, 5, E and 0, 1, 2, 3, 4, 5. And wa, which is up here, is 3060. And it's actually a different alphabet, as you see here, hiragana. So 3060, and sorry, not 60, 306. And that's the last letter in there, so that'll be 306F. And so within Unicode, we have a total of 16 bits to encode, and we can see here how we can get the numbers for each of those different Japanese letters. It is possible, if I show you, it's possible that you can actually type these in to your HTML code, and that will automatically then get the characters up for you. And so here I've got a very small snippet of HTML code, and in this part here I've put in the and the hash mean give me the Unicode character, and you need to use the decimal ones. So these are exactly the same that I worked out in hexadecimal, but I've converted it into decimal. And so 2170 is this letter down here, and then 26085 is the second letter here, and so on. So all I've done is I've told it the exact code which I want in Unicode, and then in HTML the browser can go and display that. You may or may not find this works on your computer depending on whether you've got the Japanese fonts installed. So that was my Unicode there, and the only thing to think about having looked at that is how many characters can I store in double byte or 16-bit Unicode. And so if we have a little think about it, we've got 16 bits, which means that we have 2 to the power of 16 available. So the number of bytes which we can store in double byte, so 16-bit Unicode, is 65,536. And so that covers us for languages like Japanese and Chinese and all of those characters.